Hello everybody, my name is Rishi, and today I'll be walking through solving DeepML problem number 19. The problem is implementing principal component analysis. So our task is to write a Python function that performs principal component analysis from scratch. So we get an input of a NumPy array, and where each row is a sample and each column is a feature. And we also get an input of k, which is the number of principal components to return as a tensor. So input data with shape samples, features, and k. Okay, now our function should first standardize the data set. So let's put that here. We have to standardize it. What it means by standardizing, we need to make it have a mean of 0 and standard deviation of 1. So standardize data set, mean 0, standard deviation 1. Okay. So the next thing to do after standardizing the data set is compute the covariant matrix. Find covariant matrix. Okay. Following that, the instructions tell us that we need to get the eigenvalues and eigenvectors. So get eigenvalues and eigenvectors. Okay. And then we need to return the principal components, where the principal component is the eigenvector that can correspond to the largest eigenvalue. And k represents the number of principal components to return. However, between those two, we first have to fix the signs of the eigenvectors, because an eigenvector can be in any direction, like negative and positive. You can have one eigenvector that is v and one eigenvector that's negative v. So it gives us a rule where if the first element, the absolute value is greater than 1 times 10 to negative 10th, which is like, make sure it's not 0, then if that element is negative, multiply the entire eigenvector by negative 1. So fix eigenvector direction, and then we return top k principal components. And that is the end. Okay, and we use numpy.linearalgebra.eig for eigendecomposition. However, I will be coding this in PyTorch, so we'll just use torch.linalg.eig for this. They give us an example. We can walk through this once we have code, but now that the entire flowchart is done, we can just get right to this. So to start out, because I'm working in PyTorch, I need to convert the data to a tensor. So we get an input of a NumPy array. So to convert that to tensor, we do data t equals torch.tensor of data. And then we also want to transpose this. So what transposing will do, it'll flip the rows and columns. So features are the rows, and now samples are the columns. So now number one, we need to standardize the data. So the standardized data equals the data t minus torch.mean of the data t, where dimension equals 1. So what this does is, in the calculation for torch.mean, we would be subtracting data t, so features comma samples now. So features comma samples. And then we'd subtract from that the torch.mean of data t over the last dimension, which is dimension equals 1. So that would effectively compress the samples dimension when we take the mean of it. So torch.mean would give us just the features comma 1 as the shape, which is why this would be a calculation we can do and not an error. After that, we should unsqueeze it so we have a 1 in the last dimension, because torch.mean would erase the last dimension, so it would erase 1, and then we unsqueeze it to add 1 at the end, and then PyTorch, when it does subtraction, it will add the samples dimension back in if there's a 1 present. I can walk through the math after typing this down. Now, after doing that, we could divide by torch.standard deviation of data t at dimension equals 1, and then unsqueeze it at dimension equals 1. Okay, let me walk through the shape calculations here. So, data shape is samples comma features. Data t shape is features comma samples, because we transposed it of transpose. So torch.mean data t dimension equals 1 gives a shape of just features. Okay, it erases the samples dimension because it erases the last dimension. Now, unsqueezing that, unsqueeze on that last dimension means we get a shape of features comma 1. PyTorch then sees 1 as the last dimension, and shape and the math being data t minus torch.mean data t dimension equals 1 dot unsqueeze dimension equals 1 means shape math would be what is it? Features comma samples minus features comma 1, and PyTorch compiler will automatically make it so this 1 can turn into samples and subtraction can happen. And the same thing is true for torch.standard deviation. Unsqueezing at 1 means that we have features comma 1, and then the division will meet PyTorch compiler figures out how to solve the shapes there. Okay, so that is step 1. Step 2 is to find the covariant matrix. Find covariant matrix. So there's actually a very good PyTorch function for this. So torch.cov for covariant matrix, and we put in the standardized data. Boom. Okay, that's step 2. Step 3, we have to get the eigenvalues and eigenvectors. So we can use torch.linalg.eig with the covariant matrix. This returns a tuple of the eigenvalues, comma, the eigenvectors. And they will be in lists. There will be lists. So it'll be a list of eigenvalues and a list of eigenvectors. Or like tensors of eigenvalues and tensors of eigenvectors. Not lists, it'd be tensor, sorry. So the 4th step is to fix the eigenvector direction. So we need to loop through each eigenvector in the eigenvectors list. So loop through each eigenvector in the tensor of eigenvectors. And why we need to do that is the way to fix the signs is saying that for each eigenvector we have to find the first element with absolute value greater than 1 equal 1e negative 10, and if negative, multiply by negative 1. So for eigenvect in eigenvectors dot t. Now, notice dot t here for transpose. we transpose eigenvectors because the samples would be the rows. If not, transposing means that the eigenvectors are the rows now, so then we can access them. Okay, now let's create a Boolean mask of the items in each vector that match the condition. So create a Boolean mask of items in each vector that match the condition. So mask equals torch dot absolute value of the eigenvector greater than 1e negative 10. Okay, and create a list of the indices of the true value. So the true val indexes equals torch dot non-zero of the mask. So what this does is the mask essentially gives us a tensor, or I think it's a list, a list, sorry, of all the values inside this eigenvector we've taken that are greater than 1 to the negative 10th power. The absolute values of those. So if we had a eigenvector that was like negative 1, 1, 0, 1, then mask would be true, true, false, true. Because absolute value of 1 is greater than 1 to the negative 10th. Same for 1, not true for 0, and then true for 1, This true val indexes, so torch.non-zero on this mask will give us a list of the indexes that have true that are true in the mask. So if the mask is true, true, false, true, see example above, then true val indexes would be equal to 0, 0, 0, 1, and 3. So we don't count false because false is technically 0. So non-zero would get rid of it. But true, we get the indexes of those. Okay. Now check if there is at least one match in where a value is greater than 1e negative 10. Torch dot. Okay, so if true val indexes dot numal is greater than 0, then if that value is negative, make the eigenvector negative, and true val indexes of 0, and then 0 is equal to the index of the true value. And the true value just refers to anything that true value is a number which the absolute value is greater than 1e to negative 10. So if the eigenvector of true val indexes 0, 0 is less than 0, then eigenvector times equals negative 1. Okay, that was the hard part. Now we have to return the top k, principal components. Yeah, okay. So the way to do this is we just sort the eigenvectors or eigenvalues. Sort eigenvalues greatest to least, and get the indices of those. So the way to do this is a very nice function called torch.arg sort. So indices equals torch.arg sort of the eigenvalues descending equals true. Descending equals true means we get it from greatest to least, and argsort gives us the indexes from greatest to least, not the values. And so now we get only the top k indices. So indices equals indices, and then until k. And assemble the results from the eigenvectors. So the results equals eigenvectors across the samples dimension, okay? Because eigenvectors have shape samples, comma, vectors. So we have across samples dimension, and then of all the indices that are top k. And now return. So return results. Okay. Let's see if this works. Okay. There seems to be, oh, I see a typo. So true val indexes. Oh, I put an N there. And okay. Let's see now. Okay. And our program works. So yeah, that's principal component analysis. Really the most difficult part about this is shapes and understanding how the math works out for each shape. So like specifically, remember that in PyTorch, the first dimension, like dimension equals 0, is reserved for the batch dimension. So always samples will be first and then features, which is why we want to use transpose and dimension equals like 1, for example, or 0 to determine what we're actually talking about when we pass a command in. And that also explains why we have a colon here, because we want to go across every sample and get only the vectors that are top k according to the indices list above. Yep. As always, the code for this will be in the description below. I'm just going to push it to GitHub right now. Alright, thank you.